Hi, so in this video we're going to start talking about a power series. So a power series is going to be centered at a point. Up here I'm saying a power series centered at x equals a. That means that you're going to have these powers of x minus a to the power of 1, x minus a to the power of 2. And here, we didn't write it, but of course right here you can think of it, you have a factor of x minus a to the power of 0, right? But I don't need to write that term because it's just a 1. The c's are constants, so my cn is a constant. So here is a constant c0, here a constant c1, a constant c2, and so on. Of course, if it's centered at 0, then this simplifies a little bit because you don't have to write the minus 0 in this term, and it looks just like at the bottom, right? So the cn's are here, and you only have x minus a becomes x minus 0, so you have x squared and x to the 0 right here also inserted. You don't need to write x to the 0 because that's a 1. Now, some convention we're using right now, that's not easy to understand as a definition, but we have to agree that this is going to be, we're going to think about it, that you can plug in a 0 in this case, and it will all make sense. 0 to the 0 would be 1. Okay, because when x is 0, all these terms you want them to make sense, and if you put it as a formula over here, you're plugging in 0 to 0. If I put it over here, I don't need to write it down and don't have the problem, but just be aware that we're kind of implying that if you encounter a 0 to 0, you're thinking it is 1, which makes no sense in other contexts. Okay, so what is this telling us? So the basic power series that every textbook has to start thinking about these ideas are, well, let's think about the most simple power series would be if I use the easiest thing I can think about is if I put C1 equals C2 and make it all equal to 1, and then I just have x to the n, right? So, and why is this important? Well, this is a geometric series, and where we're going with this in a couple of sessions is we're going to want to define a function to be this power series. And in that idea, what would be the domain of this function? Well, the domain of this function would be all values for which the series becomes convergent, right? So you want to put all the values such that the series is convergent. Because if you think about it, what we're saying is that once you plug in an x in this series, in this function, you're going to have a fixed value of x in here, and that's going to give you a geometric series, right? In this case, a geometric series. So that series is going to be convergent or not. And we know what that works, right? This is a geometric series, and we know that this is a geometric series, and we know that it will converge only if and only if the absolute value of x is less than 1, right? Because then now my r is my x. So that would be my domain of this function. In this context over here, that would be the domain of the function. Thinking about over here, this would be for this power series, it will be convergent if the absolute value of x is less than 1. So we're going to call this in a minute the interval convergence. So the interval convergence would be -1 to 1. And we're going to call the center, the distance from the center of the interval to one of the ends, the radius of convergence. Okay, so we have an idea of a little bit of what this is, where we're going to with this. So this is the theorem we're going to be using for all these questions, all topics in this topic, and we're going to we're not going to prove it. We're just going to use it. And the theorem says that for any power series, there are only three chances. Either the series converges only at a point, the series converges for all values of x, or there is a number, like in my last example, for which x minus a, if x minus a is minus r is less than r, sorry, x minus a is less than r, the series converges, and if the distance between x and a is greater than r, the series diverges, right? So, the thing about the first one is saying, first of all, notice that if you plug in here x equals a, all these terms are 0, right? So 0 times whatever is 0, and it's always going to converge, right? It's always going to be a number. So that's why it's guaranteed that this series will converge at least at a point, always, right? At x equals a. That's the first thing. Now, let me give you an example where this series will converge only at a point. So for that, let's use this example. Let's do this power series. So my coefficients Cn is n factorial. Okay. So how am I going to decide for what values of x will this series converge? Well, we have the ratio test. And the ratio test says that this series will absolutely converge if we take this limit of the an plus 1 term divided by the an term in absolute values, and we call that L. And if that L is less than 1, the series converges. If the L is more than 1, the series diverges. So on this one, if I use the ratio test, using x as my still a variable, I will have the limit when n goes to infinity of the an plus 1 term over the an term. These are positive terms. Sorry, not positive terms. Only the factorial is positive. The x, I don't know if it's positive. But I'm going to write the n plus 1 term is n plus 1 factorial times x to the n plus 1. And this is n factorial divided by x to the n. I have absolute values. So this simplifies to n plus 1 times x to the n. I have it like this, but the truth is, since the n plus 1 is positive, I can just put it right here, right? And I can really just put it inside the x. Sorry, this is wrong. Not x to the n, but x to the 1, right? Okay. Okay, so what does this limit go to? Well, the x is not part of the limit. Who's going to infinity in this limit is n. So the absolute value of x part is not the limit. This really becomes x times the limit when n goes to infinity of n plus 1. And this limit goes to infinity. So no matter what value of x is, this whole thing goes to infinity. So we're saying right now that this will never converge because this goes to infinity unless, since the beginning, like I said before, x was 0. So this example only converges if x is 0. Only converges at x equals 0. Because for any other value, this will be infinity. Okay. Okay. Let me just do quickly an example that will converge for all values of x. An example for number 1. An example for number 2 would be, well, this is going to be an example that we're going to talk about later, x to the n divided by n factorial. Okay. So here I did n factorial times x to the n, and doing x to the n divided by n factorial equals 0 to infinity. So let's do the same argument if we use the ratio test. If we use in the ratio test, we would have we need to find the limit when n goes to infinity of the an plus 1 term. So I'm going to write it like x to the n plus 1 divided by n plus 1 factorial, then divided by the nth term, which is x to the n divided by n factorial, all this in absolute value bars. So I need to flip the denominator. After a while, we'll do this in one step, but the first examples, I'm going to write them like this. So the denominator comes flipped in the front, so the n factorial goes to the top, the x to the n goes to the bottom. And now what I'm going to do is simplify this. And now what's going to happen? Now it's backwards. I still have the x to the n over here, which I could put in absolute value bars if you want. Sorry, not x to the n again, x, right? And the n factorial with the n plus 1 factorial cancels, and I have an n plus 1 in the denominator, right? So I still have the absolute value bars here, and again, who's going to infinity is the n, so this becomes absolute value of x. Let me write it down here. So this becomes the absolute value of x. Sorry, that looks like a less than. No, I wanted it to be, oops. Okay, I want it to be equal sign. And this becomes that limit, which is 0. Now it's the opposite of what happened over here. This limit is 0 regardless of the value of x. Right, so no matter what value of x is, this will give you 0. So when you get that, this is saying that I don't care what value of x you plug in. This limit will always be 0. So that means the series will converge for all values of x, like we had up here. Okay? So, that example for number 2. And an example for number 3 is exactly the example I had before. Right? So this is the example for number 3, the one we taught in the previous slide. Just x to the n converges if x is less than 1. So in that case, my a is 0 and my r is 1. Right? And it will diverge if it's more than 1. So r, this number r is called the radius of convergence, and the interval convergence is the set of values for which it does converge. Okay, on the next videos I'll make some examples using this theorem.